This object is a marvel of engineering. It is a window to the cosmos. A tool that reveals microscopic life. It corrects the very biology of our eyes. And you are probably holding one right now. It is a lens. A deceptively simple curve of glass. But this simplicity hides a secret. A story of extreme precision. A journey that bent the path of light, and with it, the arc of human history. This is the untold story of the lens. How a piece of polished glass gave us sight. And how it truly built the modern world. Act 1, The World Made Clear. Our story begins not with a flash of genius. It begins with a quiet observation. Sometime around the year 1000. An aging monk leans over a manuscript. The words have become a blur. His working life seems over. But he has a tool. A lapis legendi. A reading stone. It is a simple segment of a glass sphere. Likely made of quartz or beryl. He places it on the page. The letters magnify. They snap back into focus. This is the fundamental principle of optics. Refraction. Light travels in a straight line. But when it passes from air into a denser medium like glass, it slows. And it bends. A convex curve bends the light inward. It converges the rays to a focal point. Our eyes perceive this as magnification. The reading stone did not create new information. It simply made the existing world visible again. For nearly 300 years, this was the limit. A tool for the page. But in 13th century Italy, something changed. In the secretive glass workshops of Venice and Pisa, an anonymous craftsman had a revolutionary idea. What if the lens wasn't placed on the page? What if it was held before the eye? This single shift gave birth to the rewrote d'ogli. The disc for the eyes. Spectacles. This was not just magnification. This was correction. As humans age, the lens in our eye loses elasticity. We can no longer focus on near objects. The condition is called presbyopia. It was a biological deadline. A limit on the productive life of a craftsman, a scholar, a merchant. Spectacles erased that deadline. Master artisans could work for decades longer. Knowledge could be read and transferred by an aging population. The economic and social impact was immense. It was a quiet revolution, worn on the face. These first lenses were crude. The glass was filled with impurities. The curves were ground by hand, by trial and error. Each pair was a unique, imperfect creation. But they worked. They proved a profound concept. Humanity could use an external tool to fix its own physical limitations. We could engineer a better way of seeing. And this was only the beginning. Act 2, The cosmos revealed. For centuries, two lenses were the standard. One in front of each eye. But in the Netherlands, around 1608, a new configuration appeared. A new patent was filed by a spectacle maker named Hans Lippershey. He put one lens in front of another. The device was a calker. A looker. It made distant objects appear closer. News of this spyglass spread across Europe like fire. In Padua, a professor named Galileo Galilei heard the rumors. He did not see the device. He simply understood the principle. Within a day, he had built his own. And he would build better ones. Then, Galileo did something that no one else had done. He pointed it not at enemy ships or distant towers. He pointed it at the night sky. What he saw would shadow the foundations of his world. He looked at the moon. It was not a perfect, ethereal orb. It was a world. Covered in mountains and valleys. Craters and seas. He looked at Jupiter. 4 tiny stars appeared beside it. Night after night, they moved. They were not stars. They were moons. They were orbiting Jupiter. Not everything orbited the Earth. He looked at Venus. It had phases, just like our moon. This could only happen if Venus orbited the Sun. The lens became an instrument of heresy. A tool that dismantled a 2,000-year-old worldview. Humanity was not the center of everything. The telescope revealed our true place in the cosmos. But the view was imperfect. Galileo's lenses were plagued by problems. Bright objects had colored fringes. A rainbow-like halo. This is chromatic aberration. Different colors of light bend at slightly different angles. They don't all meet at the same focal point. The image is smeared. There was also spherical aberration. Lenses ground with a perfectly spherical curve don't focus light perfectly. Rays hitting the edge of the lens focus at a different spot than rays hitting the center. The result is a soft, blurry image. The quest to see farther became a quest for a perfect lens. This quest drove the next wave of innovation. In the 18th century, English optician John Dollond solved the color problem. He created the achromatic lens. It was not one lens, but two. A convex lens made of crown glass was cemented to a concave lens of flint glass. The flint glass bent light more powerfully. It was shaped to reverse the color separation of the crown glass. But it didn't cancel out its magnification. The result was a sharp, color-neutral image. It was a system. An engineered solution. The age of simple lenses was over. The age of optical systems had begun. Act 3, the engineered eye. By the mid-19th century, lens making was still a craft. An art based on experience and intuition. That changed in one small German city. Jena. Here, a mechanic named Carl Zeiss wanted to build the best microscopes in the world. He knew his instruments were limited by the lenses. He hired a brilliant physicist. Ernst Abbe. Abbe was not a craftsman. He was a scientist. He refused to rely on trial and error. He believed every aspect of a lens could be predicted by mathematics. He derived the formulas that defined optical resolution. The physical limits of what a lens could ever see. But their calculations demanded new materials. Glass with specific, predictable properties. They partnered with a chemist, Otto Schott. Schott melted down new recipes of glass. Over and over. He developed dozens of new optical glass types. Low dispersion glass. High refractive index glass. Each with precisely documented properties. This was the Jena Trinity. Zeiss, Abbe, and Schott. Mechanics, physics, and material science. They transformed lens making from an art into an industry. An exact science. They established the blueprint for every modern optical company. But a new challenge emerged. Every glass surface reflects light. About 4% of light is lost at each surface. In a complex microscope or camera lens with 10 or 20 surfaces, more than half the light could be lost. The image becomes faint. Full of flare and ghosting. The solution was almost invisible. A breakthrough from the 1930s. Anti-reflective coatings. In a vacuum chamber, a microscopic layer of material is deposited on the lens. Often magnesium fluoride. The layer is just a quarter wavelength of light thick. Mere nanometers. Light reflecting off the top of the coating is out of phase with light reflecting off the glass surface. The two reflections cancel each other out. Instead of reflecting, the light passes through. It is an elegant piece of physics. A layer of nothing that allows everything to be seen. This brings us to the modern era. To the most ubiquitous lens in human history. The one in your smartphone. This is the pinnacle of optical engineering. A story of extreme miniaturization. Look inside a modern smartphone camera module. It is not one lens. It is a stack. 5, 6, sometimes 8 or more individual lens elements. Each with a specific purpose. Many of these lenses are not spherical. They are aspheric. Their curvature changes from the center to the edge. This complex shape corrects for distortions and aberrations in a tiny amount of space. Grinding an aspheric lens was once a monumental task. Now, they are mass-produced by the billion. Molded from glass or polymer with nanometer precision. This system is a ballet of materials. Some elements are low dispersion glass. Others have a high refractive index to bend light aggressively. Every surface has multiple layers of advanced coatings. Each tuned to specific wavelengths of light. All of this is packed into a module just millimeters thick. The result is an image sharper than anything Galileo could have imagined. But the glass is no longer the final word. The lens has a new partner. The processor. Today, we have computational photography. The lens captures the light. The sensor converts it to data. And powerful algorithms rebuild the image. They instantly correct for the last remaining distortions in the glass. They merge multiple exposures to create stunning dynamic range. They analyze depth to artificially create the blurred background of a portrait. The lens is now a hybrid. Part glass. Part silicon. It is a computational eye. We began with a simple stone. A tool to make blurry words clear. That journey led us to spectacles that doubled our working lives. To telescopes that revealed our place in the universe. To microscopes that uncovered the unseen engines of life. And finally, to a computational camera in every pocket. A lens is more than a piece of curved glass. It is the embodiment of human curiosity. A relentless drive to bend the rules of reality. To see more. To see farther. To see clearer. It is the secret that gave us our modern world. Because it changed the very meaning of what it is to see.